Quantum mechanics is a part of physics that tells us how the things that make up atoms work. It also tells us how electromagnetic waves like light work. It is a mathematical framework for much of modern physics and chemistry. Quantum mechanics help us make sense of smallest things in nature like protons, neutrons, and electrons. Next, our group, Lisa, Naiya, and Ploy, going to inform you about quantum mechanics.
Quantum theory. It is a theoretical basic of modern physics that explains the natures and behavior of the matters and energies on the atomic and subatomic level. Niels Bohr and Max Planck, two of the founder fathers of quantum theory, each received a Nobel Prize in Physics for their work on quanta. The speed of wave is equal to the product of its wavelength and frequency, and is independent of its intensities. For the formula, speed of wave is equal to the wavelength multiplied with wave frequencies. In this equation, wavelength is measured in meters and frequency is measured in hertz, or number of waves per second. Therefore, wave speed is given in meters per second, which is the SI unit for the speed. Speed of electromagnetic waves are waves which can travel through the vacuum of outer space. An electromagnetic wave transported energy through a vacuum at a speed of 3 multiplied with 10⁸ meters per second. A speed volume commonly represented by the symbol c. For the formula, speed of electromagnetic wave is equal to wavelength multiplied with wave frequencies. Based on the measures and experiments, they use methods to calculate the speed of light. So they prove that light is faster than the sound. So, for the example, lightning will appear first and followed by the thunder. So the speed of light will equal to 3 multiplied with 10⁸ meters per second when in a vacuum. It is the same for electromagnetic wave. Quantum energies. In chemistry and physics, quantum refers to a single packet of matter or energies. In particle use, it refers to the minimum amount of energies required for a change, or the minimum volume of any physical properties in an interaction. Formula: energy is equal to Planck constant, which is 6.62 multiplied with 10⁻⁻34, and then multiplied with frequencies. For the next, we will move on to the property of wave. For the first one is frequencies. Frequency is the number of waves that pass a fixed place in a given amount of time. For the SI unit is equal to hertz, which you can see from the picture below. The low frequency is equal to the long wavelength. It means fewer waves and have a low sound. For the high frequencies is equal to the short wavelength. It means a lot of waves and have a high sound. For the next is wavelength. Wavelength is mean distance between identical points on consecutive wave. For the SI unit is equal to meters. Wavelength have two types, such as shorter wavelength and longer wavelength, which you can see from the pictures. So for the next is amplitude. It means the distance between the origin and crest of the wave. The SI unit of amplitude is the meters. The amplitude have two types of them. For the first one, in high amplitude is equal to round sound, and the low amplitude is equal to weak or soft sound.
Let's start with Maxwell's equation. Maxwell's equation describes how electric charge and electric currents create electric and magnetic fields. They describe how an electric field can generate a magnetic field and vice versa. In the 1860s, James Clerk Maxwell published equations that describe how charged particles give rise to electric and magnetic force per unit charge. The force per unit charge is called a field. The particles could be stationary or moving. This and the Lorentz force equation give everything one needs to calculate the motion and classical particles in electric and magnetic field. The first equations one to calculate the electric fields created by a charge. The second allows one to calculate the magnetic field. The other two describe how fields circulate around their sources. Magnetic fields circulate around electric currents and time-varying electric fields. Next, the Planck constant. The Planck constant links the amount of energy a proton carries with the frequency of its electromagnetic wave. It is named after the physicist Max Planck. The Planck constant is a fundamental physical constant. It is written as h. The Planck constant has dimension of physical action, energy multiplied by time, or momentum multiplied by distance. In SI units, the Planck constant is expressed in joule seconds. In SI units, the Planck constant is exactly 6.62607015 times 10 to the power of negative 34 joules times seconds. Scientists have used this quantity to calculate measurements like Planck length and Planck time.
When light energy in the form of protons or particles strikes a metal with sufficient energy, then electrons are ejected or emitted from the surface of the metal. This is known as photoelectric effect. Electromagnetic radiation can push electrons free from the surface of a solid. A material that can exhibit the photoelectric effect is said to be photoemissive. Electrons ejected by the photoelectric effect are called photoelectrons. The photoelectric effect will not occur when the frequency of the incident light is less than the threshold frequency. Different materials have different threshold frequencies. Most elements have threshold frequencies in the ultraviolet region of the electromagnetic spectrum, and for Einstein, photon is a particle of light. The equation is energy equals Planck's constant times frequency. Laws of photoelectric effect. Photoelectrons are ejected by a metal surface when the frequency of incident radiation becomes equal or greater than the work function of the metal. The number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation, and the maximum energy of photoelectrons do not depend on the intensity of incident light, but relies on the frequency of light. For Bohr's theory of the hydrogen atom, he extended the idea of energy quantization, and the potential energy of the electron in hydrogen atoms also quantized. Each type of atom has its energy levels at different values due to its unique number of protons in the nucleus, and electron will transition from one energy to another level when a photon of a very specific energy is either absorbed or emitted by the electron, and levels depends on the Rydberg constant in following equation. Using the equation, we can predict the wavelength of photon associated with any possible transition for the hydrogen atom, and from frequency we can get wavelength.
Fun fact: did you know that a sun made of bananas would be just as hot as the original sun? But what makes the sun hot? The sun is hot not because there is a massive fire on it. Rather, it is hot because of its immense weight. Thus, its gravitational pull is enormous, putting it under tremendous pressure and causing nuclear fusion. So if the sun were made of banana of such a colossal weight, it would be just as hot as the original sun.